All right, so the fundamental theorem of algebra says that every non-constant single variable polynomial, so I don't want f of x is equal to 3. That's a constant polynomial, so I don't want these. And then single variable, I'm only going to deal with one variable, typically x, with complex coefficients. So complex coefficients doesn't mean that they're imaginary. It just means that I could have any kind of real number, rational or irrational, but it's going to have at least one complex root. Again, not necessarily an imaginary number, although we can get some imaginary numbers, but it has to have at least one solution. So we know that the degree of the polynomial is equal to the number of roots, and I would say it's equal to the number of complex roots. All right, so also every non-zero single variable degree and polynomial with complex coefficients has counted multiplicity exactly in roots. So exactly what I just stated here. So we've talked about the fundamental theorem of algebra, but we didn't have it as a formal proof with the fundamental theorem of algebra. So this helps us solve lines, graph lines. It helps us with exponential functions. It helps us with quadratics, although we did in Algebra 1, but we didn't talk about in Algebra 1 because you weren't quite ready for it yet. So the fundamental theorem of algebra kind of tells us three things. It tells us that every polynomial with complex coefficients has a complex root. So remember, like complex numbers can be written in the form a plus bi. So my coefficients for a polynomial will not be real, but will not be imaginary, sorry, but my complex roots could be imaginary. And remember, whenever I have imaginary solutions, they always come in pairs. So I can have 2 imaginary solutions, or 4 imaginary solutions, or 6 imaginary solutions, but not 3. All right, so every polynomial of degree n with complex coefficients has n roots counting multiplicity. So always count your multiplicity. So if we have x equals 0 3 times, we can write it out 3 times, or we can say x equals 0 with multiplicity of 3. So the multiplicity tells you how many times that number occurs. It is super important to denote the multiplicity, because if you just tell me that x equals 0, I might think that I have a linear function. Right? But if I have x equals 0 3 times with a multiplicity of 3, I know that I have a third degree cubic function. All right, then every polynomial of degree n with complex coefficients can be written as a product of linear terms using complex roots. So in the Delta Math from yesterday, there were some questions where they asked you to find the equation for a polynomial function. So if I have this point as -5, 0, so I accidentally went below the x-axis, so I'll make this point as -2, 0, and then this point at -1, 0, and then I can find my y-intercept. But if I want to write this in factored form, so I have 3 solutions, x equals -5, x equals -2, x equals -1, I can write these as factors. So this would be x plus 5, moving the 5 to the other side, x plus 2, my pen's going to run out of ink, and x plus 1. So I could write these as a product of linear terms. Okay, let me just throw out that pen. Plus 2, x plus 5. Now I might have some a value here that I may need to deal with. Right, so that was kind of dealt with at Delta Math. Finding that a value, we'll answer questions for that in a few. But I can write them as a product of linear terms. What if I have an imaginary solution? I'm so glad you asked. So if I have a polynomial function that looks like this, I have one real root. So let's say this is -5, 0. So I have x equals -5. And then let's say I have 2 imaginary solutions, because I need 3 solutions because it has degree 1, 2, 3. So let's say I have x equals 3i and x equals -3i. I can write these imaginary values as linear factors. So I won't ask you to factor using imaginary numbers, but you may need to write factors as linear factors. So this f of x, we'll have some a value. I'll have an x plus 5, and then I need to set these to the other side of the equals. So I'll have x minus 3i and x plus 3i. So good news, when I multiply these together, my imaginaries will go away, and we'll do an example like that. So all it's saying, if you know the roots, you can write them as linear factors, even if they're imaginary numbers. Okay, so I have some examples. Without a graph, but finding the least degree polynomial with the given roots. So it's least degree because I don't want to make up any extra solutions if I don't have to. So looking at number 1, I have x equals 2. I have x equals 4. And I have x equals 5. Am I missing any solutions because I need to come in pairs? Feel free to use the chat. The answer is no, I'm not missing any terms or any solutions because of things coming in pairs. That was mild. Okay. So I can turn all of these into linear factors. So x minus 2, x minus 4, and x minus 5. I'm going to multiply these out. So I want to write this in standard form. So right now I'm in factored form. So this is factored form. I want it to be in standard form, which I'll write over here. So for standard form, I just need to multiply. So, all right, so I'm going to multiply these together. I can only multiply 2 things together at a time. So I'm going to leave this first factor, x minus 2, and I'm going to multiply these 2 together, and then I'm going to simplify. So x squared minus 5x minus 4x plus 20. I'm going to rewrite that where I combine like terms. X squared minus 9x plus 20. All right, then I'm going to distribute this x minus 2 here. So starting with my x, I'm going to have x cubed minus 9x squared plus 20x. And then distributing my negative 2, I'm going to write it underneath so my terms match up. So I have a negative 2x squared, a positive 18x, and a negative 40. So when I combine like terms, I have x cubed minus 11x squared plus 38x minus 40. Here's my polynomial function. Least degree, I was looking for 3 solutions, so I'm looking for degree 3. There we have it. I can always check this with my graphing calculator to make sure that it has x-intercepts at positive 2, positive 4, and positive 5. So x to the third minus 11x squared plus 38x minus 40. And then if I graph it, I'm looking for positive 2, positive 4, positive 5. And that works, right? So we did this in Delta Math with the graph, and now I'm just giving it to you with some whole number roots, all right? So we'll talk on Monday about imaginary numbers and square root numbers. I feel like it'd be better if we did these in person, but something to point out, imaginary numbers always come in pairs. So for the second problem, I have an I for a solution. If one solution is I, what is another solution? Feel free to use the chat. Yes, good job. So imaginary numbers must come in pairs. So if I have a positive I need to have a negative I. All right, so I can write these as linear factors. We'll do this on Monday. Get there. All right, so with my radical value, if I have 2 plus the square root of 3, in order to get this solution, I probably use the quadratic formula. When we use the quadratic formula, we usually get 2 solutions, especially if my determinant, the number underneath the radical, is not 0. So if I had 2 plus the square root of 3 as an answer, what is another answer that I have to have?
2 minus the square root of 3.
Absolutely. Look at you guys. So imaginary numbers must come in pairs, and radical / irrational, because they are irrational with the radical, numbers must also come in pairs. All right, so we'll work on those, multiplying those out on Monday. Any questions before I stop the recording? All right, so we'll finish up these notes on Monday and then look at the rational root theorem.